So our main topic for today is Newton's forward and backwards or backward difference formulas. Newton's forward and backwards difference formulas for interpolation. We're still talking about function interpolation. We're doing that this week. We're still doing it next week. More about function interpolation next week as well. This topic is the exact same thing we did on Tuesday, divided differences in special cases. Okay. And we end up coming up with nice formulas. Well, depending on your definition of nice, for doing interpolation that you might say are maybe a little bit more easily programmable. Maybe in Python or maybe in Mathematica. Still can be done in a spreadsheet, though it's not necessarily easier in a spreadsheet. So recall again that we are given, as usual, n+1 nodes, effectively n+1 data points, x0, y0, x1, y1, through xn, yn. The nodes, technically speaking, are just the x coordinates. The y's are function values. So there's some unknown function, yi equals f of xi, some unknown function f that we're trying to interpolate here. We are implicitly assuming the nodes, the x's, are distinct, n+1 distinct nodes. The y's are not necessarily distinct. In general, we know from the beginning of chapter 3 that you've got a Lagrange interpolating polynomial of degree at most n that will interpolate these points exactly. Typically, it will have degree n, though sometimes it could have degree less than n. If these were all on the same line, then it would be a linear function. It would have degree 1. The formula you would use with the Lagrange polynomial would simplify. All the nonlinear terms would cancel in that case. Initially, you would write it as an nth degree, but everything except the linear parts would cancel if these all happen to lie on the same line. When we talked about Neville's method and divided differences so far, the x's, x0 through xn, do not have to be equally spaced, and they did not have to be even in order. Neville's method and divided differences still works, even when they're not equally spaced and even when they're not in order. Though most typically you imagine them as being in order, at least maybe not equally spaced. Today, we are assuming they're equally spaced and in order from least to greatest. Today, we assume x0 is less than x1 is less than x2, etc. Today, we're assuming this. We have not to this point. And they're equally spaced. X1 minus x0 equals x2 minus x1 equals x3 minus x2, etc. equals xn minus 1. We could call those differences, these distances between the successive points, delta x. That would be a common notation, like in calculus for integration. Or another common notation is h, and that's what our book uses, is h. Let h be that common distance, xi minus 1, no matter what I is. I equals 1, 2, etc. through n. That also would be the same as the right endpoint xn minus the left endpoint x0 divided by n, right? Does that make sense? Think about a picture. Here's x0, here's x1, here's x2, x3, etc. xn. Xn minus x0 would be this entire distance. N is really the same as the number of subintervals. This is feeling like integration, isn't it? From calculus. N is the number of subintervals. There's the first subinterval. Its right endpoint is x1. The second subinterval, its right endpoint is x2. The third subinterval, its right endpoint is x3, etc. The last nth subinterval would have a right endpoint of xn. The second to last point there is xn minus 1. H is the entire length divided by the number of pieces. That is the length of each one of these subintervals here. Our goal is the same. Given these data about some unknown function, or maybe a known function like e to the x or sine of x or something like that, that you're trying to interpolate, we got some value of x that we're trying to interpolate the function at. Maybe x is right here or something. We'd like to approximate f of x. We could do the same things we've done so far. We could use Neville's method. We could use divided differences in a spreadsheet, say. With Neville's method, remember, think conceptually here. Neville's method was about using a bunch of linear, then quadratic, then cubic, then quartic polynomial approximations, using the appropriate number of nodes. And it's sort of like an averaging. If you watch that extra videos I talked about, it's Neville's method. The formula for Neville's method is really averaging, weighted average of some polynomial values. So ultimately get what you hope is the best highest degree polynomial approximation to the function at x. With divided differences, which we still focus on today, we still talk about divided differences today. We had a spreadsheet, and we were looking at the nth degree, or what was most likely an nth degree polynomial right away. And the divided difference formulas gave us numbers in the spreadsheet where the numbers on the upper left to lower right diagonal of the triangle shape in the spreadsheet were the coefficients in the expanded form of the polynomial. And then we use those coefficients being multiplied by x minus appropriate nodes to get our approximation. We're really using the final polynomial in that case. That's how conceptually Neville's method and divided differences are different from each other. What was that divided differences formula? The interpolating polynomial was written as P of x. Initially, we wrote it with some a's as coefficients. I'll go ahead and do that first. Again, a0 plus a1 times x minus x0 plus a2 times x minus x0 times x minus x1. And then that pattern continues with higher and higher degree terms. A3 times x minus x0 times x minus x1 times x minus x2, etc. And the last term was an nth degree, so its coefficient could be called an. It's got n factors, x minus x0 times x minus x1 times x minus x2, dot, dot, dots with those products. The last product, the last factor in this product is x minus, not xn, but xn minus 1. Remember, this has to be most typically nth degree. At least at first, you imagine it's going to be nth degree, but maybe it could be lower degree when things cancel. So this last product has to have n factors. Since the subscript starts at 0, the last one's got to have a subscript of n minus 1, not n. Where is xn? Well, you don't need it. I mean, it's in the background. It goes into the calculation of the a's, but you don't need it in the formula that you write like this. This formula worked even if the xi's were not in order. numerical order, though now we are using it when they are in numerical order. And what were the A's? The A's were the divided differences. So the A0 was the first divided difference, written like this, which is the same we saw as the function value at x0. A1 was this first divided difference. And that thing was f of x. Well, okay, it was a divided difference of 0th divided differences. I will go ahead and use the square brackets. But realize again, since these are 0th divided differences, they are also function values. The next coefficient, the A2, was a second divided difference. And it's here that the iterative recursive nature of what's going on is apparent. That's a divided difference of first divided differences. It's this, let's see, x1, x2 minus fx0, x1, all divided by x2 minus x0. The pattern continues until the last term. It's not an infinite series here. The last term, and put down here, is an nth divided difference. That is a divided difference of n minus first divided differences. You'd have an xn there, but it gets multiplied by, don't have space, the same thing we multiplied by before. This one where the last subscript is n minus 1. The notation's kind of weird. It's just something you got to get used to. So we want to work on getting used to it. But again, what are we going to do now? What we're going to do now is with Newton's forward and backward difference formulas, we're going to rewrite these formulas in some different ways. The divided differences are still going to be there. What's going to change is the nature of these products. In the special case, where the x's are in order and equally spaced, and we have this new quantity h. Before we do that, though, we should realize x can be written in terms of, for example, x0 and h. Think about it here. With this particular drawing, x is going to be x0 plus maybe about 2.8 times h. Doesn't that look right? Go to the right from x0 by 1, 2, and maybe about 4/5 of an interval here, 0.8, 80%. That x looks like it's, say, x0 plus 2.8 times h. Just making that up. Making up the 2.8 because that's what it looks like it is about. In general, for an arbitrary x, given x in the interval from x0 to xn, using interval notation there, choose s so that x equals x0 plus s times h. Such an s will exist. In fact, it'll equal, s will equal x minus x0 divided by h. We can check that. In fact, check it here. x0 plus the fraction x minus x0 divided by h times h. The h's divide out. You get x0 plus x minus x0. That simplifies to x. So this S definitely exists. It's x minus x0 divided by h, which would be 0 if x happened to equal x0. Otherwise, it is positive. H is positive. We're not dividing by 0. If we write x in this way, we can rewrite the polynomial p of x. I'm going to go ahead and use summation notation now to save some time. As f of x0, the zeroth divided difference as x0 plus a sum. K goes from 1 to n. What would it be here? Think about what we've done before, like when we're adding up these terms here. When k is 2, for example, we'd go to the third divided difference, which has a last subscript of 2. And with the products here, we'd multiply by x minus x0 and x minus x1 when k is 2. Assuming that pattern continues, we'd have a kth divided difference notationally looking like this, with the last subscript of k times x minus x0 times x minus x1, etc., through x minus xk minus 1. There's k factors there. These divided differences, remember where those come from. Those are in the table in the spreadsheet. Those are the upper left to lower right numbers. Or I shouldn't say lower right, I should say middle right in the triangular form of the spreadsheet. And if we replace x here with x0 plus sh, let's see what happens. So f of x0 plus sh, just replace all the x's with those things. Oh, let's see. So we'd get a bit of pain to write. X0 plus sh minus x0. I'm plugging into the first factor there. X0 plus sh minus x1, etc. The last factor is going to be x0 plus sh minus xk minus 1. But then those things can be simplified. xi in general is x0 plus ih, right? x1 would be x0 plus h. x2 would be x0 plus 2h. The I here is acting like the s for one of our nodes that we're using. x3 would be x0 plus 3h. So I can make those substitutions in place of those things here and get what? P of x0 plus sh is f of x0. Sorry about all the things to write here. I think it's worthwhile. We are going to get a bunch of cancellations of the x0s, won't we? In fact, in each one of those factors, the x0 ultimately is going to cancel. Here it cancels just by itself, so to speak, and you're left with s times h. With the next factor right there, when you replace x1 with x0 plus h, the x0s still cancel. You would end up with sh minus h, which is s minus 1 times h. With the next one, which I did not write, replace x2 with x0 plus 2h. X0s cancel. You're left with sh minus 2h. Can you see that in your mind's eye? You'd be left with s minus 2 times h. And with the last one, right here, replace xk minus 1 with x0 plus k minus 1h. Once again, the x zeros cancel. You're left with sh minus that. That's going to simplify, if you think about it carefully, to s minus k plus 1 times h. We're almost to Newton's forward difference formula here. In various forms. We're going to write this in various forms. So, what do we get now? Simplify this. There are k factors of h. H gets raised to the k power. With the s's, it's an s times s minus 1 times s minus 2, etc., through s minus k plus 1. What does that feel like? Something you've seen before. I'm thinking last fall or maybe the previous fall for all of you. Prob and stats. Factorials related, at least. In fact, if we do a little trick, we could write it as s times s minus 1 times s minus 2, etc., through s minus k plus 1. And let's divide that by k factorial. Of course, I can't do that willy-nilly. I have to compensate by multiplying by k factorial as well. And then don't forget about your h to the k power. Doesn't this seem worse? Well, it depends on your definition of worse. That is the same as s choose k. So it's actually, in some ways, better. But wait a minute. How can that be s choose k? S, like for this picture, is 2.8. How can you do 2.8 choose k? Is that allowed? Yes, though not in the way we usually think about combining. If s is an integer greater than or equal to k, this does happen to equal the classical formula for probability and statistics and maybe discrete math. S factorial divided by k factorial times s minus k factorial. If s is not an integer greater than or equal to k, which in our application here, it often is not, it almost always is not, you can't write this in the usual sense at least, but you can still write that, and you can still call it s choose k. All right, so we got an alternative formula here involving factorials, so to speak, or binomial coefficients, might prefer, and factorials. But there's one more step that goes on here. One more simplification. It turns out, I'm not going to go through the derivation of this. That oops, I made a mistake here. It turns out, scratch that up. That this can be rewritten in yet one more way. It turns out that these divided differences times these things are values of the forward difference operator applied higher and higher powers to f of x0. It turns out you can write the summation as the summation of s choose k times delta to the k power, which means apply the forward difference operator k times, to f of x0. when k is 1, delta of f of x 0, I'm not really applying delta to the entire sequence here. I'm applying it to the first term, so to speak. It's going to give me f of x1 minus f of x0. When I apply delta squared to f of x0, it's going to give me delta of f of x1 minus delta of f of x0, which is the same as f of x2 minus f of x1 minus, in parentheses, f of x1 minus f of x0, which can, if you want, be simplified to f of x2 minus 2 times f of x1 plus f of x0. That should feel a little familiar from Aitken's delta squared method, etc. I'm not proving this. And in fact, the book doesn't prove it in completely either, that these two things are the same. They hint at it by pattern recognition that it works. It's at the bottom of page 126. It's actually not too hard to follow. It's not nearly as hard as some of the other proofs in the book. But I'm skipping over why that works. Let's confirm it will work now in a spreadsheet. Let's apply to the sine function. So we're going to interpolate the sine function. We'll do it with divided differences as we talked about on Tuesday. And we'll do it with this forward difference formula. And then hopefully we have time to do a little bit backwards difference formula too. Let's say we're trying to interpolate the sine function using these nodes. Notice there are 6 nodes there, x0, x1, x2, x3, x4, and x5, that are 0.4 apart, equally spaced. So h is 0.4 here. What should we pick for x? Well, anything you want really between 0 and 2. Let's pick, how about 1.1? What's the actual value of the sine function at 1.1? It's about 0.891207336. Let's go ahead and do the divided differences as quick as we can here. Remind you of that. So the 0th divided differences are the function values at these nodes. So sine of these numbers. Sine of 0, 0. Sine of 0.4 is about 0.389, etc. 1.6 is not too far from pi over 2, and so this is close to 1. Quickly doing the divided differences as a matter of review, you should still be able to do it for this assignment. The ordinary divided differences. Remember, so for the first divided difference columns, we're taking divided difference of the 0th divided differences. Copy and paste that down in these spaces in between. For the second divided differences, we do a similar kind of thing. Take divided differences of the first divided differences, where what we divide by is now more widely spaced. Remember doing this on Tuesday. Next one, this minus this over this minus that, getting even more widely spaced with the denominator. Hang on here, getting close. And then finally, the 5th divided difference is this. And then remember what we did with these numbers. Again, upper left, middle right, those numbers end up being coefficients of the interpolating polynomial in the form we've expanded in, the a's. The divided difference is the f of square brackets. So if we were going to use those to quickly estimate sign as we did on Tuesday of this number, we would do f of x0, which is 0, but I'll type that anyway, plus the first divided difference times x minus x0, plus the second divided difference times x minus x0 times x minus x1. Oops. A10. Easy to make a mistake here. Third divided difference is in cell E11 times x minus x0 times x minus x1 times x minus x2. Take a breath. Hang with me here, hang with me. Plus fourth divided difference, F12 times x minus, type the same kind of stuff here. Oops, I didn't try not to make typos like I just did there. B2 minus A10 times B2 minus A12 times B2 minus A14. Just one more. G13 times B2 minus A8 times B2 minus A10 times B2 minus A12 times B2 minus A14. One more times B2 minus A16. And we never used A18 where the 2 was. There we go, pretty close. Okay, with the forward difference formula, how does it work out? So the H is 0.4. These need to be equally spaced. What we did just a minute ago worked even if the X's are not equally spaced. But here, to use Newton's forward difference formula, they are equally spaced. I'll just type the H's, that difference. S, think about it here. We had a formula that I wrote down by hand. S is going to be that x minus x0 divided by h. What should that be here? How many intervals does we have to go forward to get to 1.1? 1 interval, 2 intervals, 2.75 intervals to get to 1.1? 2 3/4. S is x minus x0 divided by h. This should be 2.25. Yeah, or 2.75. Yeah. So what's our estimate now with Newton's forward difference formula? So I'm about to use this form of it. You know what? For sake of simplicity, you can do binomial coefficients in spreadsheets, but I think I'll just do it this way. With n equal to 5 here. So the last one is when k is 5, I'll have an s minus 5 plus 1 is s minus 4. I'll just do that. F of x0 is still in B8 plus, okay. We do still need to use the first divided difference. I'm going to use this formula, so I still need these divided differences. The first divided difference is in cell C9. See that there? C9 times S. I'm using this part of the formula with k equal to 1. K is 1. S minus 1 plus 1 is S. I'm only going to have just a factor of S and one factor of H. Times H, C3. The next divided difference is in cell D10, at the very bottom of the screen there. I'm using this now with k equal to 2. I'm going to have an S times S minus 1, and I'll have 2 factors of H, H squared. S D3 times S minus 1 times H squared. Next, I do k equal to, what did I just do for k? I just did k equals 2. Now we're doing k equals 3. We need what? E11, I can't see it on the screen. Times D3 times D3 minus 1 times D3 minus 2 times C3 cubed, H cubed. Plus 2 more terms. Fourth divided difference would be an F12 times D3 minus 1 times D3 minus 2 times D3 minus 3 times C3 to the 4th. See, we're probably not going to get to the backwards difference formula today. One more term plus G13 times D3 minus 1 times D3 minus 2 times D3 minus 3 times D3 minus 4. This is where k is 5 times C3 to the 5th. Well, maybe we still can fit the backwards one. So if I enter this, we should get the same thing we got in cell C1. We should get 0.891195,404. Yes. For an error of actual minus approximate on the order of 10 to the negative 5. But wait a minute. Shouldn't we use the forward difference operator? Shouldn't we use this simpler formula? Sure, why not? I didn't test this ahead of time. Does binom work in spreadsheets, or maybe choose? Okay. No, I think it's equals combin. This combination is like 5 choose 2. Does that work in a spreadsheet if the top number is not an integer, like 5.2 choose 2? It's saying it's sort of working, but that's the wrong thing. So I think it's not doing what we want it to do. Okay. So we do not want to use combin in a spreadsheet here when we're doing this. Here's another table where we can now use the delta operator. Do the simpler formula. Take the zeroth divided differences and bring those down, although these are equally spaced, only one cell apart, so I better do this. Apply the sine function to all these. Now, just do the difference operator, just like I showed you in the first part of the class today, like this. And copy and paste these over, do the delta squared column and the delta cubed column and the delta to the 4th power column and the delta to the 5th power column. And the numbers we need are the numbers across the top. That's the higher powers of delta applied to f of x0. Those are the numbers that we need in this formula right here. So once more, the estimate should be f of x0, 0 plus. It'd be nice if combin worked, but it seems to not work. S choose k. What was S again? S was 2.75. I'll just type in 2.75 this time. Choose 1 is just 2.75. Times delta to the 1st power of f of x0. That is that number. Plus S choose 2. 2.75 times 1.75 divided by 2. 2 factorial. Times the delta squared operator applied to f of x0. Yeah, I think only time for forward difference. I was excited that maybe I could do this quicker, but next, k is 3. S choose 3. S times s minus 1 times s minus 2 over 3 factorial. 2.75 times 1.75 times 0.75 divided by 6 times DE22. Then K is 4. S choose 4. 2.75 times 1.75 times 0.75 times negative 0.25. S minus 3 is negative 0.25. Divide by 4 factorial is 21 times F22. One more term. 2.75 times 1.75 times 0.75 times negative 0.25 times negative 1.25 divided by 5 factorial times G22. Drum roll. What is this supposed to be? 0.8 to what was it? 99 or something? Yay! 0.899195404. Yes. We're doing the same thing in different ways with different notation. We got 5 minutes left. Let's just look at the formula for the backwards difference one. Though I will not have you do it for this assignment. Instead of using the delta forward difference operator, you do end up using the nabla backwards difference operator. Nabla Pn is Pn minus 1 instead of Pn plus 1 minus Pn. You do start n at 1, though, instead of 0. It is really the same sequence, again, just with the subscript changing. The labels change. The first term in the sequence has a subscript of 1 instead of 0. But it's the same list of numbers as with the forward difference operator. You can do it inductively. You can raise nabla to the k power, meaning apply nabla k times. In the end, you can derive the formula to look like this. Or with summation notation, like that. However, before you try to understand what this means, you need to realize something. When deriving this formula, we think about the nodes going not from least to greatest, but from greatest to least. Notice that's an f of xn instead of an f of x0. F nabla to the k power applied to f of xn, not f of x0. And it turns out the s, you can still solve for s in the same way. The formula for s is still this, but it ends up being a negative number. No, it's not that formula. It's you replace x0 with xn. It's a different formula. Replace x0 with xn in both spots here, and the s ends up being a negative number in that case. If x is in this interval, x minus xn will be less than or equal to 0. H is still positive. H is still the length of each subinterval. Makes s negative, and x equals xn plus sh, where s is negative. Coming back here, that means negative s is positive. Negative s choose k is then done the same kind of way we just did. You also do have to multiply by negative 1 to the k power, it turns out. So your signs in your summation alternate plus, minus, plus, minus, plus, minus. Not going to assign it. It's not that much harder to use, really. As far as the spreadsheet goes, there's 2 ways to do it. And I will talk about this next Tuesday. You can either make a similar kind of divided difference table, but make the nodes go in the opposite order, greatest to least. Or you could use the same table, but instead of using the numbers on the upper left to middle right, you use the numbers on the lower left to middle right. instead. And down here, if you switch the order, you still use the numbers across the top row. Or if you use the table as it is, you use the numbers on the bottom instead. Quick summary of what to expect. Talk about it next Tuesday. Have a good day and a good Easter.